Sorry about the formality of all this, but it saves me getting my hands too dirty, but we'll do some multimedia work as we go along. So I think I'm going to be probably skating over things a bit more than Dave did, rather than going into one particular topic, just to give you some idea of the sorts of things that have been looked at in some of the workshops and activities that have been going on with. So here's a fairly standard statistical problem, that of regression, in which we have, let's say, information about two quantities, x, which is going to be an explanatory variable, and y, which is a response variable. For instance, x might be age and y might be blood pressure, and the way it goes is on average, blood pressure tends to increase as one gets older. And what about a model for this one? Well, the simplest model that you might propose is as what's called a non-lighting laser pointer. There we are. That this is called simple linear regression. So the response is a linear function of the covariate plus error. And the statistician likes to put distributions on things, so the usual assumption about the errors here is that they're all Gaussian, zero mean, and variance sigma squared. So is the notation n 0 sigma squared familiar? Yep. So the unknown quantities are the intercept, beta 1, slope, beta 2, and sigma squared. And given the person's age, the expected value, or the average value of blood pressure for those individuals of that age is this linear function of age. Well, you can put all the equations together into this matrix vector formulation. So y is the vector, we've taken these measurements on n individuals. Y is the vector of their blood pressures, and then the expectation part of the model we can write as a matrix X times the parameters beta plus the set of errors. And if there are p parameters, then X is n by p and beta is p by 1. And the objective is to fit a straight line to the data, if you like. And one approach, the familiar approach, is to use least squares. You draw lines such that the sum of the squares of the vertical deviations of the responses from the line is minimum. So this is essentially the equation that defines the least squares estimates. There it is in terms of the matrix vector formulation using the L2 norm, and it's least squares. If we have this normal Gaussian assumption about the errors, then this beta hat is also a so-called maximum likelihood estimate. This is the formula for the underlying distribution, and obviously a beta value that minimizes the sum of squares function maximizes this. So that's it. The actual solution, the least squares estimators satisfy this equation up here, and so in principle we would hope to solve it to get an explicit formula for the least squares estimates in terms of the responses and in terms of this matrix involving the covariates, the explanatory variables. Now, if the model's correct, we've got the linear structure and the Gaussian distribution for the errors, then this beta hat actually has this distribution. So on average, beta hat does equal the true values of the parameters, That's what's called unbiasedness. And we also have, this is now a p-dimensional normal distribution. So this is a matrix, and it's the matrix of variances and covariances of the elements of beta hat. And they can be used to get interval estimates, so-called confidence intervals for the parameters of the line. So this is a very simple situation, simple linear regression. It turns out that in much greater generality for maximum likelihood estimation, at least approximately, provided you got a lot of data, the distribution of the maximum likelihood estimators is Gaussian, again, centered on the true values of the parameters, whatever they happen to be, and with some sort of so-called covariance matrix here. And typically, the variances, let's say, of the estimators tend to 0 as the sample size tends to infinity. So that's it. Oh no. Sometimes it's not so easy. If we don't have a number of observations bigger than the number of parameters, this matrix is bound to be singular. In fact, sometimes it's singular even when p is less than n. So if it makes sense. If we're estimating more things than we have data for, roughly speaking, we get into trouble. So we can't actually directly write down beta hat, and the so-called asymptotic theory, what happens as n tends to infinity, isn't guaranteed to work. So what if we have applications where like the size of the model is bigger than the amount of data, or even a lot bigger? For instance, you have a sample size of 50 and tens of thousands of potential explanatory variables, either in regression or some other situation. And that's, if you like, one of the basic aims of our program is to worry about that sort of scenario, because it's becoming a very common one in real applications. So here are 2 or 3 applications: microarrays, climatology image analysis, where you've got images with 1 million pixels. In a sense, each pixel could be thought of as being an explanatory variable. Using textual analysis to classify documents. Now the diagram, oh yes, the diagram is to draw you a microarray.
Oh
my. That has got about 1,000 little spots on it, each representing a gene. So, and quite often you'll have an actual real array where you've got up to 12 of these. So you could have tens and thousands of values from each of these little spots, indicating the so-called expression level of a gene. And you might have a comparatively small number of these measuring the DNA of people with a certain illness, and another comparatively small number measuring the DNA of people who don't have the illness. And what you want to know is which of these genes are going to be good at discriminating between the ill people and the non-ill people. So it's slightly different from regression. I will mention this a bit later on, but it's sort of like regression when the response is a binary variable, ill or not ill. But you certainly have lots and lots of potential explanatory variables. So what do you do about it? Well, going back to the regression problem, one thing you can try is to say, well, all right, if X transpose X is singular, let's tweak it so that it's not non-singular, And if I put a little bit of the identity matrix onto it, I do create something that I can invert. And this leads to something called ridge regression, which is not a 21st century development, but it certainly leads to an estimator for the parameters of the straight line, or the so-called linear model. It does introduce bias. If I worked out the expected value of this beta r hat, I wouldn't get the true beta. It's got on average, it doesn't quite get the right answer, but its so-called variability is spectacularly, well, if I didn't have that in, and I had a singular x transpose x, in a sense the uncertainty about it would be infinite. So just putting a little bit of the identity in collapses the variance dramatically. Well, I just kind of, I've written that down out of the blue in a way, just to get something that's non-singular. But here is another way of looking at the, another way of creating the ridge regression, namely to minimize this so-called penalized sum of squares function. You've got the sum of squares function, which we're trying to minimize before, and we've added on lambda 2 times the squared Euclidean distance of beta from 0. And this can be regarded as L2 regularization. It could be called penalized least squares or penalized maximum likelihood. And it's also got what's called a Bayesian interpretation. So I'd maybe better say something about what the Bayesian approach is. The Bayesian idea is to put probability distributions on unknown quantities that are not really random. So what this is saying is that this is the basic Bayesian relationship. Supposing that this P of beta represents my uncertainty about beta before I gather any data, I then gather my data y according to the model for y, and this is really just putting it through Bayes' formula, Bayes' theorem for getting the conditional distribution of beta given y in terms of the conditional distribution the other way around, basic formula. And this is called the posterior distribution of beta, posterior to having done the experiment and gathered the data y. This is the prior, then with the data we get the posterior. Now this is our Gaussian distribution, and we put on our Gaussian distribution for beta. It turns out that the posterior density for beta is proportional to the exponential of something like this. And maximizing this is equivalent to minimizing that. So it does have a so-called Bayesian interpretation. Now, a few decades ago, there's great controversy about this Bayesian approach, because we've got two completely different types of distribution here. This has a so-called frequentist interpretation. We can think of repeating the experiment and getting different sets of data, and if we do that a lot of time and draw histograms and things like that, then the histograms will look a bit like that. There's nothing frequentist about this. This is not the result of experimentation. This is your personal belief. So these are completely different types of objects, and yet the Bayesians are happy to put them together and see what happens. And the other problem is that my personal beliefs might be quite different from yours. So my posterior, pardon the expression, might be quite different from yours. And people worried about that. Now I think that's died down. Anyway, that's a bit of a digression. But the ridge regression estimator has a Bayesian interpretation if you feel like you're a Bayesian statistician. Now, once you write it down like this lambda 2 looks awfully like a Lagrange multiplier. Therefore, there are two more interpretations of the ridge regression estimator. As a minimizer of the sum of squares function subject to some constraint on the L2 norm here, or minimizing the L2 norm subject to a constraint on the sum of squares function. So there are lots of interpretations of this particular estimator. And it's certainly computable in theory, but this is still a large matrix. It could still be 20,000 by 20,000, which is not very convenient. So the idea then is to say, well, although P is bigger than N, we can't really believe that you can get away with having a model which has got vastly many more parameters in it than we have data. So we seek what's called a sparse solution for beta, and that's one in which there are lots of zeros. So how are we going to achieve that? Well, one way of doing it would be perhaps to say, well, perhaps go to here and say, this zero norm is just the cardinality of beta. So it's the number of non-zero elements in beta. So let's say, put a limit on the number of non-zero parameters that we're going to insist on, and minimize the sum of squares function. In other words, what this is really doing is minimizing the distance between the model, as represented by this, and the actual data. Well, if we start with this particular formulation, there are going to be two more. One of which is to say, well, for a certain Lagrange multiplier, this problem is solved by minimizing this quantity here. Or we could go to this one, minimize the, maximize the sparsity of beta. If you say sparsity is having a small number of non-zero parameters subject to a constraint like that. So we've gone from L2 regularization to L0 regularization. The problem with this is it's not practically feasible, because you really you've got to look at all possible 2 to the p ways of picking out subsets of the parameter vector and look at them individually, and then pick the one that solves the problem. So we'd like to solve this problem, but it's not very easy to do. So split the difference. What about L1 regularization? Well, that would mean solving this sort of problem, where the L1 norm is the sum of the magnitudes of the elements of beta. And here are the obvious two alternative interpretations. Well, this particular problem and its solution is called the lasso, and it's rather amazing to what extent it dominated talks in the workshop we had in January. The computation is pretty comparatively feasible. It's essentially quadratic programming. And a simple geometrical picture suggests it should lead to sparse solutions. Oh, I better draw it. So the picture compared with L2 regularization, it says, well, we've got this sum of squares function, and it defines some ellipses. And the L2 constraint, supposing we said the L2 constraint on beta, that really means that we've got to be inside or on this circle. So the solution is going to be something like that here. And both the parameters are going to be non-zero here. On the other hand, the typical L1 constraint, I'm not drawing this in a helpful way for my own purposes, but typically the solution to the L1 problem is a corner of this particular feasible region. So in general, in very high dimensions, it's going to be a corner where a lot of the betas are zero. So that's why we hope to get a sparse solution out of the L1 problem. So what are the main aims of the technique? We want to identify exactly which components of beta are zero and which are not. And the ones that are not are called the supports of beta. And then once we've decided that, we want to know what are the actual values of the non-zero elements of beta. So we want to find the ones that are zero and estimate accurately the ones that are not zero. And we'd like to do it as well as we'd be expected to do if we were told beforehand exactly which of them were zero and which were not zero. And this is called the oracle property. So here are a few comments on what people have done with the lasso and the variants of it. This page really goes slightly different. Is slightly different from the lasso. This is what Candace and Tao call the Danzig selector, and they approach it by the formulation involving starting with minimizing the L1 norm subject to a constraint which isn't, it's still a constraint that represents the difference between the model and the data, but it's not quite the same as the sum of squares constraint. Don't worry about the details of the notation, but what they show is that this particular approach, which is not slightly different from the lasso, does, if the true number of non-zero elements in beta is less than the sample size, then the so-called oracle property obtains with overwhelming probability. I mean, there's lots of technical conditions and impressive analysis behind this, but that's basically what they're saying. And then David Donohoe and Tanner looked at the so-called noise-free case and said, well, supposing that this were exactly right, and supposing that we define a sparsity ratio, k is the true number of non-zero betas, n is the sample size, and supposing rho is the ratio of sample size to number of parameters we put in the model, then there's a kind of phase transition phenomenon as to how this particular problem can be solved. And they produce a diagram something like this. This is delta up here, and this is rho. So this is the cardinality of, well, the number of non-zero elements in beta divided by n, and this is n divided by p, and they have a curve which is something like this. And basically, they want to know what chance have we got of actually solving the problem of interest. And it ends up that if we're down here, the probability is 1, and up here the probability is 0. This is a kind of that's a limiting diagram. They did lots of numerical work for non-limiting situations, and they found their results were kind of hovering around that particular theoretical curve. So, I mean, qualitatively it's reasonable that you would expect to do better down at the bottom than up at the top if you think about it. But it's interesting that there is this this cliff that you fall off if you're not far enough down.
Is that I didn't pick up when I heard David Donohoe speaking about that, but I didn't pick up whether that was an inevitable and intrinsic character of the problem, or the approach to the problem. You with me?
Well, I mean, it relied on certain assumptions about the way in which you generated the explanatory variables, the X matrix. But I think it was a pretty well intrinsic.
It was an intrinsic character.
I think so. Yeah.
Actually, for the noiseless case, and you expect that the heuristic applies.
I think the curves are different for different things, but
Pardon?
I think the curve is different for different situations, but
Right.
you still get the phase transition.
Right.
Well, Martin Wainwright went back to the lasso and got a rather not quite the same thing, but again, if you have enough data, then with probability 1, you will identify, using the lasso, you'll identify the solution of the L0 problem. And if n is small, is below a certain threshold, then that probability essentially becomes 0. Well, I'm going to move away now from the lasso, but still consider this problem of reducing dimensionality. And this page describes Dennis Cook's approach to this. And it's what we say at the top here is that if you're going to choose a sparse beta, you're throwing away variables, and you're choosing therefore a certain k-dimensional subspace of the parameter space. But it's a rather special one, defined by by all the other betas being 0. It's a linear subspace, but it's a rather special one. So Dennis Cook's idea is to say, well, why don't we allow different types of linear subspaces? You know, a linear subspace is a matrix times beta equals something where the matrix has got rank k, but it doesn't have to be, if you like, a partial identity matrix. And these are what he calls sufficient dimension reductions. Well, there are various ways of defining such a sufficient reduction, and the one that he concentrates on is this, which is defined in terms of the inverse regression problem, not the regression of y on x, but of x on y. And R of x represents a sufficient reduction if the distribution of, in terms of the inverse regression formulation, distribution of x given the responses and given the reduction set R of x, if that doesn't depend on the responses. In other words, it's really saying that everything to do with y is bound up in R of x. And he kind of models this using a situation like this, where the link between the explanatory variables and y is defined in terms of a matrix gamma, which is P by K. In other words, the key thing is that this multiplying vector here, which is related to y, is only k-dimensional. Anyway, that's perhaps too much detail in that. Other versions of the regression approach, you don't have to, I mean, there are lots of non-linear and non-parametric even regression models in statistics now. This is Lafferty and Wasserman's SPAM, which is supposed to mean sparse additive models. This is a so-called generalized additive model where the regression function, the function that defines the mean of y, is made up of p terms, if you've got p covariates, and the jth term is some function of the jth covariate. So this xij is the value of the jth covariate on the ith individual in the sample. So each of these terms includes only one of the covariates. But this fj is allowed to be anything, completely flexible. It doesn't have to be a polynomial or anything like that. Well, this is the generalized additive model, and what they essentially do in their work is to reduce p in a clever way to k, like try and reduce the number of terms in the additive model. Ed, George and co. have a different version called Bayesian additive regression trees, which Ed tells us he wanted to call fast additive regression trees, but he was shouted down. Again, so each term in the regression function is a so-called tree structure, and all the covariates, all the explanatory variables in principle could come into the tree structure. So I'm not, all I want you to be aware of is that there are much more subtle things around than linear functions, linear regressions. Now, earlier on, I mentioned the classification problem in the context of microarrays, where the response variable you're looking for might be just a binary variable, and in the context of diagnosis, the explanatory variables could be just clinical tests, presence, absence of symptoms, and so on, and the response variable is disease 1 or disease 2, or disease or not, or not diseased. And the objective is to get a mathematical rule for assigning new patients to one or other of the disease categories on the basis of their clinical tests. So it's differential diagnosis. And the rule is usually estimated on the basis of training data from people who you already know are either healthy or diseased. And this is what's called supervised learning, where you know your training set has got the explanatory variables and the response variables.
That's because they lived or died or something.
Well, because they're guaranteed known to be one category or the other. Yeah. Well, there are lots and lots of ways of constructing a discriminant rule, and they have to be adapted when the number of explanatory variables is vast, as in the case of the microarray scenario. And I mentioned here the so-called support vector machine because just to draw the link between the statistical activity and other ideas that have come out of the computer science machine learning area. And the simplest version of the support vector machine would be as follows. there are two sets of patients. These have got disease 1, these have got disease 2. You want a rule to decide for a new patient, is he a naught or a cross? And the simplest sort of situation, you would have some sort of a straight line boundary. If you're on this side, you're a 0, a naught. If you're on that side, you're a cross. But there are lots of these straight line boundaries. And what the support vector machine does is to find the one that maximizes the so-called margin maximize the gap, and then take that as your boundary. These are the so-called support vectors, the points that define what the margin is. Now, if this had been invented by a statistician, it would have been called an algorithm or a method, but it's called a machine.
That's the computer science influence, is it?
And you can express it in terms of constraint optimization, obviously. You want to maximize the margin subject to this lot all being down here and that lot all being up there. So I could have written down a constraint optimization problem for this too. Now, I should say you can adapt it to that situation as well, and you can make it non-straight. I mean, there are lots of developments, but that's the trivial version of it. An unfairly brief word about visualization. This is a very important area, with apologies to Ed at the back there for being so brief. I think all I want to say there is that because there are some really nice computer facilities available, it's natural to make use of them, and you can look at lots of different projections of data and discover all sorts of things, rotate data clouds, and so on and so forth. So it's important, but I just don't have time to say too much about it. Finally, say something about going back to Bayesian analysis, because this is an area where I'm going to, in the end, mention a few words that have already been mentioned today by Dave. Good to look at Bayesian analysis in missing data contexts. If you remember, this is the key equation in Bayesian analysis to combine our prior feeling, knowledge, whatever, with data to get our posterior knowledge, summarized by that distribution. Now, the normalizing constant is just the so-called marginal probability function for y, which is defined like that. Now, intuitively, this is bound to be of interest. What do we know about the unknowns after we've done the experiment? This is also potentially of interest because if we have two completely different models, and we work out these marginal probabilities for both models, then comparing them allows us to possibly decide whether we prefer model 1 or model 2. Now, the problems arise if we can't, if this isn't easy to do, or if that isn't easy to do. And if you have some missing values of some sort, then complications arise. Usually, if you don't have missing values, then the analysis is easier than if you do have missing values. Because if the z's were known, things of interest like this, well, if we knew what the z's were, they would be part of the data. So the thing of interest would really be the distribution of beta given everything. And also the so-called likelihood function, the probability function of all the data given beta is often quite simple. So how do we deal with these missing data? I say or latent data. We actually enrich a model by making it more complicated with so-called latent variables, but just think of them as missing values. This is still the main thing of interest, because y represent the data we actually have. There's no point trying to go for that, because we don't know what the missing values are. This is really what's of major interest. Now, if we did know what this was, then this would be, sorry, we don't know what this is. So if you think, well, the set of all unknowns here consists of the parameters, beta, and the z's. So the thing we really ought to be able to get from our experiment is the distribution of everything that's unknown given what we've obtained from the data. And just by simple manipulation, this is given by the likelihood, well, it's proportional to this times this. So in theory, we would be able to write it down. Now, if we knew what this was, then we could integrate out or sum over the z's, and that would give us our marginal probability function for the parameters given y. So to get around this, I mentioned two approaches. The stochastic method is to generate realizations from this, and usually using some sort of Markov chain Monte Carlo procedure. And then if we've got that, and just pick out the realizations that we've created for beta, that will be, all being well, a sample from the posterior distribution for beta given y. So you've got to generate all these observations, and using a method that has to converge before you're sure you've actually got a realization for the distribution of interest. So it can be computationally heavy, and you can be a bit uncertain as to whether you've actually got to convergence or not. The other approach is not stochastic, it's so-called variation approach, and that is to do the following. What we'd really like to know is the distribution of everything we are ignorant about given the data that we have. So what we do is we'll choose an approximation to it in some sensible way, and we'd like to choose it to be close to the target, and this is closeness in terms of what's called the Kullback-Leibler divergence, which I hope you know what it is. It's just a measure of distance between two distributions. Now we could actually make this, zero, but to do that we've got to choose qy equals this, and the whole point is we don't know what this is. Now we take our log of the marginal distribution for y. It turns out you can write it in as a sum of this quantity and the Kullback-Leibler measure, and this has one or two consequences. If we actually manage to minimize this suitably, now we're going to have to put some constraints on qy to make it feasible to work it out. But if we minimize this, then the corresponding qy maximizes this function, and this function is a lower bound for the log of py. Remember, that quantity was going to be of interest in model choice. So the best qy is one that minimizes this and consequently maximizes this. Last picture, I think, last diagram. Now, the typical structure that people impose here, you've got to make qy simple in some way, and the typical structure that's assumed is that it's a factorized model, a bit depending on the missing values and a bit depending on the parameters. And then you turn the handle. Well, comments about this. If you knew what the z's were, there are certain circumstances where the Bayesian analysis is very straightforward. If the likelihood is, if the log of the likelihood is quadratic in the betas and the log of the prior is quadratic in the betas, in other words, it's Gaussian, then the log of the posterior is also Gaussian. And that's what's called conjugacy. So there are lots of examples in what are called exponential family distributions where you have conjugate distributions. And it turns out that in the variational approximation approach, if we have that conjugacy here, then the beta factor takes that conjugate form. And it's just a matter of saying, well, which particular member of the conjugate family have we got here? Problem, the true thing we're aiming at is certainly not of this conjugate form. So you've avoided the difficulties with Markov chain Monte Carlo. In theory, the Markov chain Monte Carlo will get you as close as you like to the correct target if you do enough simulations, but it's terribly complicated. This will not really get you to the correct form, so you have to worry about whether or not this is causes you a problem. So certainly one thing that interests me is saying what happens asymptotically. If you have a lot of data, asymptotically lots of distributions tend to look like Gaussians because of central limit theorem and so on. So what's of interest is, well, what would be the, let's say, the mean and the variance of this approximating distribution as n tends to infinity? And there's a bit of work on that. Anyway, this has links to statistical physics because approximations quite often turn out to be things like mean field approximations. The difficulty evaluating the P of y is very similar to problems of evaluating partition functions. This function here is, I think, something like a free energy function, and so on. So this area, at least in terms of terminology, has links with statistical physics. Trailer for the main event next week, in which you'll get a much better story than I've given you.
Yeah, I don't believe the last statement, but David did give a good talk that I heard, so I recommend it. Like, could you just go back to 18? Because, yeah, I mean, I could, if you take that, if you think of the log Q as like your free energy, Q is kind of analogous to a partition function. So that, for me, says that the Q of Z and the Q of beta don't interact in the Hamiltonian picture, which Dave was talking about. They're not interacting, actually.
Could be.
The fact that they factorize, I think. And so I'm not surprised that you say that that is not you know, a realistic thing to assume. And the realistic thing is when they do interact, and you just have a terribly difficult problem.
That's right.
I did want to say, and this is dredging up from my past, but I mean, if you go back to what Dave said about the critical point, I mean, normally in these statistical mechanical problems, if you look at what happens in the thermodynamic limit, the large volume limit, then you recover its central limit theorem and you recover Gaussian distributions for everything. But if you're at a critical point, that you do not recover Gaussian distributions. You get quite different kinds of distributions, which can actually be bimodal, for example. I could, you know, and give you an example. I have no idea whether that touches at all what you were hinting at when you were talking about that.
Well, I don't think it does, in the sense that somehow critical points don't really get into this particular literature. I mean, one thing that we found with some simple examples about this, when we're thinking of comparison with the correct answer, we're finding that as far as the mean or the mode of this is concerned, it looks as though it gets to the right place as the mode of this. But if you're thinking about curvature, and the curvature dictates the lengths of interval estimates, if you like, if it's very sharply curved, then the interval estimate will be narrow. The interval estimates you're getting from this tend to be unrealistically narrow. So I don't think it's a, I think it's kind of smoother problems than a kind of a phase transition problem. But I mean, there are circumstances where even this is not all that helpful. In the example of a noisy image, for instance, where the y's are the actual observations, the actual observed image on the one for each pixel, and the z's are the true underlying realization. And if you assume that that comes from a Ising model, then you're stuck with a partition function all the way. You know, I haven't said anything about the difficulties that would arise if p of beta, okay, well, if it's not really p of beta, if the underlying image was thought to be a realization of the Ising model, or anything with an awkward partition function. But there's a lot of statistical and machine learning literature about problems, about approaches to estimating normalizing constants.
Yeah, if you could go back to page 17,
Mm-hmm.
please. That expression 1 that you're maximizing there looks a lot like an entropy of the distribution Q, Qy. It's got exactly the form of an entropy.
Well, part of it is, integral Q log Q is an entropy, isn't it? Yeah.
Yeah.
Mm-hmm.
So I mean, it's something analogous to the estimator being the maximum entropy estimate.
It's a relative entropy.
Relative entropy.
It's relative entropy. Yeah. Yeah, it's a conditional relative entropy that he's got there, and so it's more like a negative entropy.
Well yeah, because the Q is in the
Yeah.
denominator of the logarithm.
Yeah, you tend to use relative entropy in the continuous context because it's transformation invariant, whereas you don't get that same transformation invariance or approximation possibilities with the regular entropy. You don't get the right convergences when you discretize and want to approximate something continuous. I forget the exact problem, but it breaks down. You don't get the right convergence, whereas you do with the relative entropy. And the meaning is similar, actually, because the regular entropy is like an average code length. And this is, the relative entropy functions like the average excess code length that you've used above what you had to use. So they're very closely connected mathematically and interpretationally.
Just getting back to this question about critical points. So my impression has always been that the critical phenomena are really undesirable in statistics because they essentially correspond to estimators which have a diverging variance. So all this business with regularization or putting a pi on your estimators, isn't it the case that that's the whole purpose of that is to drive us away from any sort of criticality?
Well, it's certainly, you know, I guess we don't tend to use the word criticality, but certainly some awkward singularity of some sort.
As a Bayesian, I would say there are many other good reasons to require some things that just to avoid.
Oh, they're really interesting areas. You're trying to, yeah.
I'll join in.